Welcome back. Last time we talked about the software style, we talked about specifications, the requirements document. I really hated giving that lecture, by the way. That was not any fun. Like I said, that'll be a great thing once you become boss. On the other hand, today we're going to talk about the Internet of Things. And the next couple of lectures are all going to get us up to doing Lab 4. Make sure you do Lab 4 that's called Internet of Things and not some other Lab 4. If you want more information on what we're going to do in the next couple of days on the Internet, Yarabali and I taped a sequence of short videos on these topics. And so if you want more information, help yourself to the Internet. Okay, so as a motivation, let's assume there's 50 of us in the room, and we want to connect each one of the 50 of us to the other 49. And so if there are 50 stations here in the room, it's going to take 50 times 49 cables to connect each one of us to each other. Okay, so unfortunately this is an n-squared process such that if we try to scale the connection of the people in the world, 50 that's a big number. That's over 1,000, over 2,000. If there was 1,000 of us, then we'd have 1,000,000. If it were 1,000,000 of us, then we'd have a very large number of cables. So we'd use up all the copper in the universe just trying to connect this up. So we need a better way to connect up multiple devices. And that's our motivation here for the Internet. So the question becomes, what is the Internet? Okay? And so the way to think of the Internet is to say, what if I had a number of devices that were, say, in the same room or in the same building or close to each other? The question would be, how do I connect them up? Okay? And we already saw it doesn't take very many interconnections to be direct connections to run out of copper. So even for small numbers of devices, 10, 20, 30, 50, we're going to want to use some sort of connection to allow a scalability. So if I add one more node to this, system, it doesn't require a redesign. This is the essence of Ethernet. Okay? Ethernet is a way to connect multiple devices together. When you get to 445M, we're going to use CAN, but CAN doesn't build itself into the Internet, so I'm going to leave this as Ethernet. If I don't like my wires, right? If I don't like my wires, I could put radios in here, right? I could have devices, some of which are hardwired connected. Some are hardwired connected with the Ethernet, but others have wireless links to this protocol. And I'm going around the world and giving everybody some computers, and I'm connecting people's computers up to these local area networks. I'm connecting them up. Let's do one more. Red. Somebody who has a lot of computers, and they're all wireless. Okay, right there. And we're going to connect them up wirelessly to some sort of access point. Okay? So what's the Internet? Okay, these are all local area networks or intranets. But what we're going to have is some sort of, I'm going to draw my Internet so it looks like a cloud. Okay, we're going to have an Internet, and then we're going to need a gateway, a connection. So each of these local area networks can connect into the Internet. That's the essence of what this internet is. It's a connection. It's a network of networks. And as you know, these little blue boxes are either your cable modem or your T1 connections or T3 connections. There's all different ways to connect up. And so if I want to communicate between this computer and that computer, okay, I am going to send my data across this wireless link to the access point, and then this is going to traverse the internet until it finds a spot and get there. So this will allow me to connect, and we'll see this essence of a socket later in our talk. Okay? All right. But that's the essence of what the internet is. All right, Control C. All right. So what is then an Internet of Things? Which is the essence of Lab 4. What is an Internet of Things? Well, you know what the Internet of web pages and email and all those applications. But in this class, we're going to allow us to connect up things that we don't think are necessarily internet terminals, right? We're going to talk about an embedded system, right? And we've been doing embedded systems all lab 1. Your alarm clock is an example of an embedded system. But as you saw, your alarm clock had a microcontroller. It had some inputs. It had some outputs. Right? But in order for you to know what time it is, what did you have to do? What did you have to do to your alarm clock to program its time? Manually. You had to manually enter it in. So one of the things that the internet could do for our alarm clock is to tell us what time it is. Okay? We could have an embedded system with a sensor on it. Okay? Let's say we're measuring temperature. Okay? A temperature monitor. Let's say we have a air conditioning system or a heater. Okay? This is a controller that controls the temperature in our house. And so we can think of things that have both inputs and outputs, things that have just inputs, or things that have outputs. And the Internet of Things is to take our embedded system and connect it up to the internet. So the outcome of Lab 4 is to take your microcontroller that does something, it outputs to the display, it inputs from a sensor, and connect it up to the internet. Okay, so that we can either observe remotely what it's doing or control remotely. So all the things that the embedded system does can be connected up to the internet. That's the fun part. Now, if you're thinking about your project this semester and you're going to go, hey, John, wouldn't it be nice if my project connected up to the internet? Now, you have two choices. One is to buy yourself, if you want a project that you keep forever, one option is to buy yourself this $20 board we're going to use in Lab 4. The second is to buy a cheaper one that I showed you last time. But you're going to need that module, okay, in order to make your device connect up to the internet. Now, if you want, you can just borrow it for the semester, but you got to give that back. Okay? So an Internet of Things is essentially an embedded system connected up to the internet. Okay, that's the essence of what we're doing here. Okay. All right, so now comes the problem, okay? And that is there are a lot of issues associated with doing this. The first is standardization. And so we have to be able to build and live within a standard. Now, it turns out in 445L, in Lab 4, we're going to use a standard which is called a ultra lightweight. It's an ultra lightweight which means it doesn't take much memory, IP stack. Okay? And when we'll see it in in your code for Lab 4, every time you see the letters S, L, and unfortunately it looks like S1 because L looks like a 1 in the font, but it's SL. Every time you see an SL underline, of course these guys love their 445L because that means what in this style? That's a public function to the module, simple link is what the simple link. Okay? So we will see the standardization in this by looking at the functions, the set of public functions that begin with SL, and that will be our protocol. Here's another problem, and that is your stuff has to work with everybody else's stuff. That's part of the standard. Your stuff has to work across technologies, across devices, across manufacturers. It'll be interesting to try to get this CC3100 built by Texas Instruments to connect to or talk to this ESP8288, which is built by somebody else. And then yours has to work with, I use my cell phone as the access point into the internet. So there's an Apple thing. You might have an Android. And so this interoperability means your device has to work across technologies. Okay. Here's something that's interesting. If I say the word evolution, right? If I say the word evolution, what do I mean? Evolution is the process of what? Process of change. Okay? And if we think about how things change, they change in two ways, right? They change in an incremental, one step at a time way, and then all of a sudden somebody invented fire or the wheel. Okay, so this is G2, G3, G4, G5, and all of a sudden somebody invents G500. Okay, and we will have a huge change, a game-changing evolution. Okay, and so we have to live in this world where change is part of the process. And so how do you live in change? Well, you will live in change by having standards and having back compatibility so that your device continues to work. Okay? This stuff is used in critical situations. Stability. Okay, stability. Things have to work. Okay, it has to work in a wide range of environments, and so this is a critical problem that these devices have to live with. We are going to live in the upside down world. Okay, we've been preaching this bottom up. Approach to education. 306, you learned what a transistor was, and 319K, you introduced yourself to C, and then you got objects in 312, and now we're talking about systems here in 445L. We're going to flip the paradigm for 1 week and go top down. And so what that means is when you're done with Lab 4, you're going to go, whoa, that's nice, but I have no idea how it works. Because we only got 2 days to teach you everything about the internet, and 2 days is not enough time to teach you everything. So we're going to abstract all sorts of things. So when I talk about a socket, that's an abstraction. When I talk about an access point, that's an abstraction. So there will be this encapsulation which we are going to employ in order to get something totally awesome. Okay, so it's actually a violation of our educational objectives here at the University of Texas. But everybody, we want you to graduate knowing what the Internet of Thing is and we want you to make smart objects, and so we are going to violate that rule. And so we will live in the world of abstraction. Okay? You will see that it's scalable. Scale. Okay. And so what works with 2 computers will work with 20, will work with 20 million. It's got to work with 20 billion. Okay? And so this whole thing is a large scale. Now, it turns out the internet server that we have in 445L was one of those free ones from Google. And so if you want to bring down the whole class, just spam it. I'll run out of free tokens, and no one will be able to finish their lab. So try not to go into the millions this week doing lab 4, because Google will say no to Valvano, and then that means nobody finishes their lab 4. So on the other hand, with a little bit of money, Google doesn't care if we send them 50 million requests, because they can handle it. Okay. The last one is security, and there's really three aspects of security that are interesting for this type of application. The first is confidential. So, for instance, you are going to measure something on your object. I don't care whether it's distance or temperature or happiness. I don't care. You've got a sensor on your lab 4. That's a piece of data. You're going to push it to a 445L server. Okay? Now, you may not want anyone else to know that. Okay? That may be so private that you want to pass that data in a secure way, so that only you and I, because it's my server, know about that data. Now, we don't care, but we might care. Okay? The second is integrity. Okay? Let's say you measure something that's important and you push it to my server. We don't want anybody else in the room to modify your data. So when your data hits my server, we want to make sure it's valid. So that's the issue of integrity. And then, as you know, we want to prevent denial of service attacks. We want it to be available. Okay, especially if this data has value. We want it to be available. So you just lose a lot of money when a server goes down. You lose a lot of opportunity when things stop working. Okay, questions? Okay, that was easy stuff. All right. Control C. This essence is layered. And now there's a couple of ways to look at the layers. We are going to, if we look at the TCP/IP interface, we're going to see the layers in a couple of areas. If we start with the application layer, okay, and we're going to have a web server. That application will have a certain protocol associated with it, which will be the highest level. And then we're going to see how that application level breaks down into what's called the transport layer. For us, that's going to be TCP. Okay? So the transport layer is going to be TCP. We're going to send TCP packets. Then it goes to the internet. Okay, and there we're looking at things either TCP or UDP. TCP is reliable, predictable, and UDP is faster, but loses packets. Okay, and in here we're going to talk about the internet protocol, right? And we saw that was the UIP, that ultra lightweight one. There are some other lower protocols here, ICMP and IGMP. And then at the lowest level is the media access control. Okay. And at this point, this is the local area. This is either our Ethernet or the Wi-Fi layer. So we're going to see these layers. And so as we write our programs, we're going to identify where those layers are. Okay, we can see the layers in another way. Okay, we can see the layers in another way by looking at the messages. Okay, so for instance, I'm going to do something like greeting, spell it right, equals, let's say temperature, swiggle, 21.2 C. Okay, and so this is going to be a message which will have a field. Okay, it will have a field. This is the application layer. There will be fields of that message with your name, with your location, in this case with the data that you want to send. And so we'll develop a protocol associated with this application message. And so this part of the message is how you're going to encode the data that you upload to the server. And then the layer below it is going to be a TCP packet. Okay? And in the TCP packet, this portion of the application is going to be there, plus some header information associated with the TCP protocol. And then at the internet level, at the IP level, we're going to take this, and then we're going to add some more stuff, some IP protocols stuff to that. And then at the lowest level, we're going to take this and add more stuff. So we will see both in terms of its object and in terms of its messages, this layered approach. And we're going to basically focus in this lab, we're going to focus at these two layers. So we will look at the server protocol, and then we will create a TCP packet, which will have the IP address that we want to send it to, and the message we want to send to the server. And all the other layers are going to happen automatically because for $20 we just bought them. Okay. All right. Let's teach you some details. Let's look at this IP address, and we're going to focus on IP v4, which is a 32-bit address. The problem is 2 to the 32 is not very many, not enough, especially for some of us who hog lots and lots of IP addresses. So the way they solved it is, if you remember our first drawing of the internet. Okay, remember our first drawing of the internet is where we had multiple devices here, all connected up with some sort of local area network. Okay, and so we are going to see that, and again, this was called an intranet. And we're going to see that in the IP address. So for instance, this one might be at 192.168.1.1. All the dots mean is each of these things is an 8-bit number, right? So 8-bit, 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 32 bits. Be careful about the big and the little endian, because it obviously matters. Because 1.1.68.192 is not the same address. Okay? And so what we're going to do is give each of these a first top 16 bits that all are the same, and we'll use a bottom 8 bits for their what's called their local address. So how many nodes can I have on my intranet? Bunch, right? 65,000. Right? I have a bunch in there. Okay? But what I'm going to need is I'm going to need a connection, right? I'm going to need a gateway, what's it called? Public IP address. I'm going to need a public IP address. And that public IP address is what we're going to use to connect to the internet. Okay? And so in order for this to work, we're going to need somebody who's really smart. And it's called a network address translator. So that when a packet shows up here, this network address translation will know to which node that packet was intended. Okay? And we're going to see that's going to be built around the socket. Okay? So we're going to open up a socket here. That socket's going to have a name associated with this intranet. And so when this TCP packet comes barreling through this public access spot into the network address translator, we're going to know to where that socket is located within this intranet. And so it will then be rerouted to this local IP address. So this 198.168.1.2 is not going to be observable from the internet. It's only because I opened that socket and I'm now routing packets through this public spot. All right. So how is it all going to work? This is a picture of a typical layered hardware, because you remember the internet is layered, so you might imagine the software and hardware layers or hardware components are also layered. And so if we were looking at how a typical interface, like how your cell phone or how your laptop connects up to the access point, how it implements Wi-Fi, we will see that most of the intellectual property, most of the thought is software. Okay? So the user application, telnet, email, HTTP, that's an application, that's software. Okay? And then that goes through a protocol layer, okay, and more software, and that goes through a translator, and that goes eventually into the TCP/IP protocol, and through some more layers, and through some more software, and eventually, way down deep, there needs to be some radios. Okay, the radio is the thing that's going to transmit that packet out into the air. Later in the semester, after we get through some labs, we're going to revisit the physical part of that of this protocol. But for now, we're in big black box. Okay, and you can sort of see that what you're supposed to see from this picture is the size of the layers. Okay, that most of the implementation of a typical Wi-Fi communication is software. And so you need a very large amount of memory and a very fast computer like your cell phone or like your laptops to implement this. But we have a problem in the Internet of Things because we neither have a fast computer, let's face it, 80 megahertz is not very fast. Let's face it, 32K RAM is not a lot of memory. Okay? It's wonderful for an embedded system. It makes a great thermometer. It makes a wonderful clock. I can spin a motor, but I can't implement internet. I can't do it this way. But we want to hook it up to the internet. So what we're going to do is we're going to shift these layers from software into silicon. Okay? And we're going to simplify it. That U in the UIP is saying, well, I don't need all of the internet. I just need a little bit of it. Okay. And so the way it's going to work is we're going to do this with some hardware. Okay. It's actually a complete separate Cortex-M. There's actually another microcontroller in there with some software, but most of the actual internet Wi-Fi protocols are implemented in firmware on this $20 device. Okay? And if you want to get one for $3, then you can buy this other one. But the most important thing about getting a job done is the availability of software code. Yeah, you want to pass that one around. That's the cheaper one. That's that little board, that little green board on that protocol is this thing. But its software is not as elegant. It's not as easy to use. It's a little bit hokey. And so for Lab 4, we're going to use this $20 part because Texas Instruments gave us a boatload of starter code that says if you want to send an email, call this function. Okay, which is yeah. Or in our case, if you want to push something to the server, send this TCP packet. Okay, so we'll see really how if you'll open up the book, for instance, there's an example in the book. It's one page. There's one page of Cortex code which will fetch data off the weather. That's how simple, one book page of how simple this system is. And like I said, the way it works, it's still got all those layers. Still has a radio. Still has the media access controller. It still has drivers, except it pushed them out. And what it gave is, you remember we used the word SL. SL stands for simple link, and that is our UIP. And so we will see a set of functions that our software can call when we want to implement internet. Okay, again, so we're going to abstract out all of these layers here. And it's going to cost us $20. Okay, it's going to cost us $20. So now let's talk about some of the hardware. One of the difficulties in using this chip is it looks like it's using up all the pins, right? It plugs into all the pins, right? If you look at it, all 40 pins, right? There's 40 pins on your connector here. All 40 pins are connected up to that device. So you go, now what do I do? Yeah, all of my pins are gone. Okay, all of my pins are gone, and that's what this slide is. This is also in the lab manual. What I've highlighted in bold are the pins it actually uses to implement Wi-Fi. Okay, and if you remember, how does your microcontroller connect up to the liquid crystal display? SPI. Okay, do you remember what pins you used? The SPI pins you used? What port? What letter did you connect up your port A? And luckily for you, this one's not using port A. This one is using port B. Right? See him right there? It's using port B. There's more B over here. Here's more B over there. So it's using the upper 4 bits of port B to communicate between your microcontroller and the CC3100. So when it wants to do something on the internet, all it does is send a message from yours into it. Okay. Now there's some other pins. There's a chip select, and it actually uses the different chip select than this one. This is this is either a bug or a feature. I haven't figured it out yet. But the starter code initializes PB5 to be the frame select in the initialization, but it uses this one when it actually communicates. And when I look in the data sheet for the CC3100, the physical diagram doesn't seem to connect this pin up. But I bolded it because if you use PB5, this driver will also turn on PB5. Okay, so it's not one of the ones you can use, but you can see you have a few other ones. Now here's another thing about this that I haven't totally figured out, is there are some pins that are listed in the CC3100 data sheet, like PB0 and PB1, look like they're connected, but the software does not initialize them. The software, the starter code that we'll have for Lab 4 does not actually initialize them. So I haven't tried using it yet, but you can see, okay, and here's some more over here. There's some more unused ones here. So you can see PD is unused. Some of these, some of these are connected up internally, but not actually. There's no. It shows a connection in the circuit diagram, but the software doesn't initialize it. This semester, when you're doing Lab 4, I'd leave them alone. I mean, if you got a project and you're going to use this exact thing, then there may be a way to work around using those pins. Okay, so this part of the lecture is to remind you to look at the data sheet for this device, particularly on which pins can you use without messing it up. I remember the first demo I did; it was awesome. I was sitting in a crowd of people, and I had a little slide pot on here, a little 319K slide pot, and I was showing how smart I was. And I said, well, don't slide that slide pot all the way over to the left. And the person goes, why not? I happened to be used one of the pins so that it worked that the slide pot was on the other end. But when I pushed the slide pot all the way in, I grounded that pin, and it stopped working. This is not, don't ignore this, right? These pins are used. You're plugging it in there. Be careful not to use the same pin for two. Yeah, I know. You get old. You've made every mistake in the book. In the book. Careful of that one. All right. So, in summary, what do we have here is the internet is our way to get out to the system. We have a bunch of layers. Those layers are application, internet. Then we got the TCP, and then we get down to the physical layer. We saw that this address has got 4 fields to it, 71.22.44.0. This represents a 32-bit number, and we saw basically how this happened. Okay, and what next we're going to do is show you some demos.